All right, so we are continuing on with the central limit theorem here. Um, their section title, honestly, I'm not sure exactly what they're meaning to imply with that. What we're talking about here is basically combining the central limit theorem with what we learned last week about standard scores and probabilities, um, and using the central limit theorem to find probabilities for sample means, essentially. Um, so let's move on. So the standard score for a sample mean is essentially we take what we know about the standard score. You know, z is the x minus mu over sigma, and we plug in the new appropriate values. X bar being our sample mean, um, mu sub x bar, mu subscript x bar, being the mean of the distribution of sample means. Um, Sigma sub x bar being the standard deviation of that distribution of sample means. Right. So, assuming the central limit theorem applies, that we've got a sample size larger than 30, then mu sub x bar becomes mu, just the sample mean. And the sigma sub x bar we can replace with sigma, the sample standard deviation, divided by the square root of the sample size. I'm losing track of words tonight. Um, so let's just dive right into some examples. So according to some CDC data, and the source will be on the next slide, um, the mean total cholesterol level for people over 20 from 2007 to 2010 was 197 milligrams per deciliter. Um, so, first question is, what is the probability that a randomly selected adult, so one person, from the population will have a total cholesterol level of less than 183 milligrams per deciliter? Um, and we use a standard deviation of 35 milligrams per deciliter and assume a normal distribution for the population. Yes, hello. Um, and I've gained a little helper here. I may have to leave and make sure he can find his food because he seems to be not too competent to find it on his own yet. Second question is, what is the probability that a randomly selected sample of 150 adults will have a mean total cholesterol level of less than 183 milligrams per deciliter? Again, standard deviation of 35. Okay, so part A, single person. Part B, sample of 150 people. All right, so let's start with sketching a normal curve to help keep track of everything. We know our mean is 197, and we know that the uh, value we're after is 183, and we want to know what this probability is that the score cholesterol level is less than 183. Okay, this is the same situation for part A and part B. The only difference is being a sample or a single person. All right, so let's start with converting that 183 to a standard score. Again, this is for the individual. So our z-score formula is the one we've been using up till now. The x, the individual, minus mu over sigma. Um, so 183 minus the mean divided by the standard deviation, we get a negative 0.4. Okay, so we can look this up in the tables. Um, and we get approximately 0.3446. This guy is going to be walking on my keyboard before long, so I will be back in a moment. Okay. All right, I'm back without my little helper. All right, so we look this up in the tables. A z-score of negative 0.4 is approximately, get my highlighter back, is approximately 0.3446. So roughly a 34.5% chance of any randomly selected adult to have a cholesterol less than 183 milligrams per deciliter. Can do this in the TI-83-84 in one step. Tell it you're looking from negative infinity, basically, to 183. There's our function, normal CDF. Give it the mean and the standard deviation, and it will give us our value. Okay. All right, so moving on to the sample now, we're looking again, same situation on the graph, except we're looking at a sample of 150 instead of a single person. Okay, so we need a slightly different z-score calculation because it's a slightly different situation, so slightly different values are appropriate. So we're using this one. We're looking at the mean of that sample being less than 183. Same distribution mean, and our standard deviation now is the standard deviation divided by the square root of our sample size. So in terms of actual numbers, this bottom part is the only thing that actually changes because we're still looking for less than 183. We're just looking for an average from that sample of less than 183. Standard deviation will be the standard deviation divided by the square root of the sample size. So we get negative 4.9 for our z-score. If we look that up in the tables, that may well be off the table. They're saying it's approximately 0. Let me just double check that because I don't think our tables in the textbook go out that far. They do not. They only go to plus or minus 3.4. So that is, yeah, essentially 0. Rounded to 4 decimal places. Basically what that's telling you, again, you do need to bear in mind that that curve never actually does hit 0. So it, 5 or 6 or something decimal places out, it probably does have a value. So it's very unlikely, not technically impossible, just very, very unlikely. So it is a lot more likely to find a single person with that cholesterol than to find a group of 150 people that have an average cholesterol that low. Again, we can do this in one fell swoop in the calculator. You'll note everything here looks the same up until we get here. And here they've put in that calculation for standard deviation instead of calculating it out and rounding it a little bit and putting that in. So if you put the calculation here inside the function, it will help keep the accuracy a little bit and eliminate some rounding error. So we get approximately 5 times 10 to the minus 7th. So you can see that it is technically possible, just extremely unlikely. All right, so let's look at another example. So if men in the U.S., if the weights of men in the U.S. are normally distributed and the population mean is 194.7 pounds with a 32-pound standard deviation, what is the probability that a random group of 10 men who enter a elevator with a 2,000-pound weight capacity, what is the possibility that their combined weights are going to be over that 2,000 pounds? Okay, so we've got our mean, we've got our standard deviation, we have our sample size, and we have our 2,000 pounds, the score we're interested in. So our sample size is 10, so the central limit theorem does not apply based on sample size. However, the population was specified as being normally distributed, so we can use it. Okay, so we've got a kind of tricky wording here. So we've got 10 men, and we want a combined total of 2,000 pounds. But what we need is the average weight of those 10 men. But if the combined total is 2,000 pounds and it's 10, then our mean is 200 pounds. So it's adding a complication of needing to do the mean calculation based on what's there. So we can, based on that, we can restate it as what is the probability that a random group of 10 guys has a mean weight greater than 200 pounds. Or to draw it out to help keep track of things, there's our standard curve, there's our mean, and this is the sample mean that we are interested in, and we want to know what that area is above 200. Okay, so first step is to convert this to a standard score. We've got a sample size rather than a single point, so we are looking at the sample mean version of the standard score. So it's sample mean minus population mean over standard deviation divided by the square root of the sample size. So 200 is our sample mean, 32 was our standard deviation, 10 was our sample size, 194.7 is our population mean. That gives us approximately 0.52. Okay, so we want the area to the right of 0.52. If we go through and use the tables like we talked about last week, find the area to the left of 0.52 and subtract that from 1, we get 0.3015. So it's approximately 30% likelihood that a random group of 10 men will exceed the weight capacity of the elevator. Or again, we can do this in one fell swoop in the calculator. Set the left limit, set the right limit out to a very large number, give it the population mean, give it the standard deviation appropriate for the calculation we're doing, and we get our probability. Okay, so another example, if we've got a women's athletics shoes have a mean price of $75.15 and a standard deviation of 1789, what is the probability that a random sample of 50 pairs of shoes will differ from the population mean by less than $5? Okay, so they've added a bit of complication. Again, we're not after, we're not given the limits exactly. We're wanting plus or minus $5 here, right? So we need to subtract and add $5 from the population mean. So what we're interested in is the range between 70/15 and 80/15. Sketch that to help keep track of it. We've got our mean of 75/15. Upper limit of what we're after is 80/15. Lower limit is 70/15. All right, so let's find the z-scores. Let's start with the lower limit. We're dealing with the sample again. Our sample size here is 50, so the central limit theorem applies regardless of whether the population was normally distributed, right? So lower limit is 70/15. Population mean is 75/15. Standard deviation was 1789, right? We plug those values in and we get negative 1.98. One thing to note is the absolute value up here is the difference from the mean, period. So if, this is 5 below the mean, I'm going to get the same number with the 80.15 without the negative sign. I'm moving the same distance from both sides, and it's symmetrical, so I will be looking at plus and minus 1.98. You can do this in the calculator, as we kind of discussed. Glossed over most of the calculator stuff last week, but it's in the tables. The calculator or Excel or something like that will give you 0.9523. The tables would give me 0.9522. Again, how I would do that is find the area, the probability associated with everything to the left of that upper limit, and subtract off the probability of everything to the left of that lower limit to find that area that's in between the two. Okay, so roughly 95% probability that the average for a random sample of 50 shoes would be within that range. Again, with the calculator, you can give it the lower limit, the upper limit, the mean, the standard deviation, which goes all the way down here, and it gives you that all in one fell swoop. Okay. I believe this is the last one. So we're looking at manufacturing plant making screws. The screws are 1.625 inches long, so that's 1 5/8 inch. Standard deviation is 0.01 inches. If quality control randomly chooses 50 screws out, what is the probability that their mean length differs from the population by more than 0.004 inches? So that is less than 1 standard deviation, either side. Okay, so let's look at this. If we subtract and add the 0.004 from the 1.625, we get 1.621 and 1.629 is our lower and upper limits here. And we are interested in the area off to either side of those. All right, so again, we are going to start with converting these to z-scores. And again, because this is symmetric, I only need to convert one side z-score, and it's going to be plus or minus that z-score on either side. Right, so we're dealing with a sample. So here is our z-score equation. The sample mean minus the population mean divided by the population standard deviation over the square root of the sample size. Right? We already know our sample mean minus the mean is 0.004 because we're at 0.004 to either side. They stuck with the positive side, just less to keep track of without the negative sign, right? Standard deviation is 0.01. Sample size was 50. That gives us 2.83. So our z-scores are plus and minus 2.83. Right? We're after the tails on either side, so I can find it just on one side and multiply that by 2. If I look up that negative 2.83, in the table, I get 0.0023. I multiply that by 2, I get 0.0046. So the probability of our sample batch not meeting requirements is very small. I'm going to circle back here for a minute. You'll remember, you might not remember, I remember when I saw this, noted the tail area I'm looking for is a lot smaller than the standard deviation, and so I was kind of half expecting the z-score to be, on the order of what would that be? I was expecting it to be fairly small. However, when we're doing this calculation, this standard deviation here becomes a lot smaller. So you can't necessarily eyeball this based on the population standard deviation. It's going to throw you off, as it did me here. Again, we can do this in the calculator. They did it with have 2 times our function, from really negative infinity range to 1.621. Right, they left this in terms of without converting it to z-scores. 1.621 was our lower limit. 1.625 is the mean. Then there's that standard deviation formula so that they don't have to round anything and lose any accuracy that way, and you get the 0.0047 instead of 0.0046. It's very, very slight difference, slightly more accurate because of the lack of rounding error. Okay. And that is it for this week.